The purpose of lab number 4 is to analyze the movement of an object attached to a spring. Specifically, the motion of this object follows the path of an oscillation, with changes to both the y and x position as time progresses. After data regarding the attached object's position has been collected, a computational model is created to simulate the movement and gather information about the energy of the system. The fundamental principles that are vital in this lab are the energy principle and Newton's second law. Newton's second law is vital in this scenario as it allows for the computation of both the position and velocity update formulas that are necessary for our code. The energy principle, in its most basic form, states that the change in energy of the system is equal to the energy inputs from the surrounding. This principle relates an effect, or the change in the energy of the system, to a cause, or the interaction with the surroundings. In order to gather information about the x and y positions of this object, it is important to input certain information into Tracker. For example, the axis is oriented at the point of attachment, with the negative y direction being downwards. Also, a calibration stick is important because it provides a reference for the dimensions of this video. In this scenario, the calibration stick is from the point of attachment to the attached mass and measures 0.70 meters. This graph shows the x position of the attached mass with relation to time. Similarly, this graph shows the y position of the attached mass with relation to time. After this data is collected, the computer coding aspect of this lab can begin. First, it is important to insert known values. The mass of the attached object is 0.402 kilograms, the initial position is negative 0.108, negative 0.640, 0 meters, and the initial velocity is 0 meters per second, due to the fact that the object starts at rest. Next, the spring stiffness is 6.33 Newton meters, and the relaxed length of the spring is 0.123 meters. The next step in this coding is to specify the kinetic energy of the system, as well as the spring potential energy and the gravitational potential energy. These individual components are then added together to obtain the total energy of the system. Following this calculation, the individual forces acting on the spring are calculated within the while loop, so as to properly predict the motion of the attached spring. Also within the while loop, the total energy change is calculated in order to investigate whether or not the energy principle is satisfied in this scenario. Before running this code, it is important to input the CSV file that contains the data collected from Tracker in order to properly analyze the actual positions of the data as compared to the positions predicted by the computer code. As seen in the output, the red sphere represents the data obtained from Tracker, whereas the blue ball attached to the spring is representative of the computer coding. There is some discrepancy in the two within my resulting output, but this is likely due to human error when extracting the position data from Tracker. However, within this output, it is clear the energy principle is satisfied in this scenario. Based on the way the system was specified as the spring plus the earth, this means the change in energy of the system should be equal to 0 due to the fact that there will be 0 work done by the surroundings. This is clearly true based on the output, as the kinetic energy, spring potential energy, and the gravitational potential energy fluctuate throughout the time interval, but the change in energy by the end of this time is 0 for the total energy. When estimating how long one oscillation takes for the attached mass to complete, it is important to analyze both the x and y position data. When using the x position data, it is estimated that one oscillation takes 1.646 seconds. However, when using the y position data, the time for one oscillation is estimated to be 1.67 seconds.